So let me give you an example. So assume that T is stable. Okay, let's assume that T is a stable theory. So we can think about an external definable set in a dual manner. So let me try to draw some picture. So let's say I have M, my model, okay? And I have some external definable set. So what do I mean by this? By this I mean I have a large elementary extension N and some set defined using parameters in N. So let's say this is my Y in the earlier notation. And then X corresponds to the part of the set which lives inside of M. Okay, so let's say Y is given by some formula, phi of X B, let's say, for some tuple B in some sort Y of the bigger model M. Okay, so B is some external tuple. So now we have that the set X is definable in M, excuse me, X is going to be definable in M, if and only if the phi type of B over M is definable. Okay. By the phi type, I mean, as usual, the collection of all instances of the formula, right? So recall that this means I either take phi or its negation. So this is a collection of all formulas of the form phi of AY for a tuple corresponding to the sort X in M, so that N satisfies the corresponding truth value of phi of A with B. Okay. So there's the usual meaning of a phi type, just the collection of all instances of phi or its negations, which are satisfied by B with parameters in M. And so that the tuples match the corresponding variables in the formula. Okay. And so now we have that our externally definable set defined using some particular formula phi and some particular external tuple of parameters B is going to be definable in M if and only if the corresponding type is definable, which simply means that the set that I wrote, let's say, if I ignore the, let's say, plus or minus, let's just say this. So we have this type is definable if and only if this set, so the set of all, okay, sorry, let me write it separately. So this was just the definition of the phi type. But now we have that this happens if and only if. What does it mean for a type to be definable, right? So we're just asking that the set of all A in MX such that phi of A Y belongs to the type, the phi type of B over M is a definable subset of MX. Okay. So this gives us a dual way to think about external definable sets. So you can think about it as just the way I defined as a trace of some definable set in a bigger model, or we can think about it as a definition schema for a type of some tuple, okay, or just ignoring the tuple, just a definition schema for some type. This is the same thing. So external definable sets correspond somehow to potential definitions of types. And then in a stable theory, because of this, we know, of course, all types are definable. So it's one of the characterizations of stability, right? One of the, if you want, definitions of stability. So recall that T is stable if and only if all types over models are definable. All types over all models are definable. And so the conclusion of this little discussion is that in a stable theory, there's nothing to say. All external definable sets are already internally definable. Okay. So in stable theories, looking at external definable sets, we don't see anything new. This is just the same thing as definable subsets of models already. Okay, not interesting. So the interesting things begin outside of stability. So this becomes an interesting phenomena once we look outside of the class of stable theories. So let me give you two examples, which are going to be of very different nature. Okay, so let's say this was example 1, example 2. So what is a typical example of an external definable set? Okay, so let's say T is the theory of dense linear orders. Yeah, and let's take a model to be just the rationals with the order. Okay, so if I draw it like this, let's say, and pick some cut. So we can take, let's say, X to be the set of all A and M, so that A is less than, let's say, square root of 2, less than the square root of 2. Okay, so if I pick the cut corresponding to the square root of 2, and I'm going to take my set to be everything to the left of it in M. So this is an externally definable set. Okay, this is an externally definable set. We can use the square root of 2 as a parameter in some elementary extension, let's say in the reals with the order, which we view as an elementary extension. But it is easy to see that this is not definable inside M itself, right? Because this is, by quantified elimination, let's say, by quantified elimination in dense linear orders, we know that any definable set is just a union of intervals with parameters in M, with endpoints in M. But if you take any interval for which you're only allowed to use parameters in M, you're going to either undershoot or overshoot, right? Because the cut for the square root of 2 is not realized. You don't have it. Okay. So by QE, X is not definable in M. Okay. And of course, the same game can be played for all unrealized cuts in any linear order, right? So in linear orders, we have a lot of new external definable sets, which you cannot see from the inside. Well, you can see them in some sense, maybe, but not. You cannot define them precisely from the inside. Okay, so this is example, the first example, and another example. Example 3, let's say, is another typical unstable theory, the theory of the random graph. So let T be the theory of the random Rado graph. Okay, of the countable Rado graph. So I assume most of you have seen this before, right? So this is just the model companion of the theory of graphs in the language with a single binary relation, the H relation. You can get it as a Frassel limit. Equivalently, you can define it just by flipping a coin and saying that you have an edge, let's say, uniform coin with probability 1/2. And you get an edge if, let's say, you have tails, and no edge if you get the other thing that I forgot what it's called. Heads, if you get heads, yeah. Okay, so the theory of the Rado graph. So, okay, so again, what happens here? Well, in the theory, you have a lot of definable sets. So in fact, we get that every subset of M is externally definable. So let's say M is a model of T. Okay, then every subset of M is externally definable. Okay, and I'm only talking about subsets of M itself, not the Cartesian powers, or not some idea. Yeah. Why? Well, because the axioms of the theory of the random graph basically tell you that if you pick any finitely many points, let's say A1 through AN, and you pick any B1 through BN, and let's say all of these are pairwise disjoint, then you can always find an element, some C, which is going to be connected by an edge to all of the AIs, but not connected to any of the BJs. Yeah. And we can do it for any fixed number elements, of pairwise disjoint elements in pairwise distinct elements in the structure. But then by compactness, we can actually pick out any set we want, right? So by compactness, it follows that any subset of my M that I want, I can find an external parameter B in some elementary extension, which is going to be connected precisely to the elements in X and not connected to anybody outside of X. So just by the edge relation already, I can pick out all subsets of M. Okay, so this shows that every subset of M is externally definable. Okay, so much richer situation. Somehow definable set, even though the structure itself is relatively tame, it's simple, for example, etc. In fact, we can cut out all possible subsets using external definability. All right, so these are two stereotypical examples of failure of stability. You can either have the order property, so something like DLO, or you can have the independence property, the failure of an IP, which is something like the random graph. Okay, in both cases, you have non-definable, external definable sets. Well, by early discussion, we saw that this is equivalent to the failure of stability. If you're unstable, you do have some external definable set, which is not internally definable. But there is a big difference between these two examples. Okay, let me say a little bit more about the case of the random graph. So we're interested in something called the Shelah expansion of a structure. So let me define it quickly. So definition, given a model M of T, where T is an L theory, we're going to look at an expansion of M where we add a new predicate for every externally definable set. Okay, so given such a model, M of T, the Shelah expansion of M denoted sometimes in Shelah, sometimes in literature. In the literature, you see it denoted as a mixed. Is an expansion of M where every externally definable subset is named by predicate. Every externally definable subset is named, every externally definable subset of every power of M, let me be clear. So every externally definable subset of M to the N for all N is named by a new predicate. Okay. And in fact, let me do it in a bit more explicit manner. So I'm going to tell you a particular way to take such an expansion, where I want the names of the predicates to reflect something a little bit about the formulas of T, the L formulas, which I use to define them. So more precisely, I'm going to choose some N, an elementary extension of M, in L, in the original language, so that this is going to be M plus saturated. Okay, so I want all types over M to be realized in N. Okay, and then we define the language L prime, which is going to be the language of the Shelah expansion, to consist of predicates of the form R. And now I'm going to plug in some particular formula with some particular parameter. And this is going to have the same three variables, where phi of x, y is an L formula, and B is some tuple from N, the corresponding sort of N, okay? So this is going to be my language. For every, and the idea that I want to interpret these predicates as defining the set given by this formula when intersected with M. Okay, so where in M Shelah, I'm going to interpret this. Okay, so this is going to be the set of all A in Mx, so that n satisfies phi of A, B. Okay. So I'm just adding a new predicate, naming every externally definable set. And in my language, I'm keeping track of which formula was used to define it. Okay. So of course, note that there might be many repetitions. It's possible that the same externally definable set is defined by many different formulas, by many different instances of the same formula, or even by many different formulas, right? We can always add something dummy, like some dummy variables or some dummy conditions. So there are repetitions, of course, in this language. Also note that the model M itself gets named by constants here. So note every element of M is now definable over the empty set in the Shelah expansion, right? So the original model is named by constants. And so this language L prime is also potentially large. I mean, it's at least the cardinality of M itself, right? Why every element is named by a constant? Well, because you have, of course, singleton definable sets. They in particular externally definable. And so we added such a predicate symbol for each of them. Okay. Okay, so this is Shelah expansion. Right? So we just throw in all the externally definable sets into the picture, and we want to see what happens. Okay. And two very different things happen in these two examples that I gave you, the case of linear orders and the case of random graphs. So let's inspect what this gives us in the case of the random graph. Okay, so is it okay if I scroll? Because I don't seem to be able to do it. I can only jump.
Yeah, this is fine.
Yeah, okay. So let's return to this example, the random graph. So the claim is that, so remember, T was the theory of the random graph. M is an arbitrary model of T, okay? And I'm going to look at the Shelah expansion. So let me denote it by T prime from now on. So this is going to be the L prime theory of M Shelah, okay? So the expansion by all externally definable sets. Okay, so then the claim is that T prime does not eliminate quantifiers. Okay. So somehow, once we add externally definable sets, it's possible to define more sets by taking projections of those onto some of the coordinates. And somehow the complexity of the theory we cannot control. So it gets worse. Yeah. Well, one particular manifestation of this is that there's no quantifier elimination. Okay, so this is a fun exercise actually to see why. Maybe I sketch it maybe. So why is it the case? Okay. So the idea is going to be, first of all, so step one, we can find. Yes, question?
Cat meowing. I'll close my.
Oh, okay. Okay. All right. So the first observation is that we can find a countable clique, or let's say maybe anti-clique, it doesn't matter. Let's say anti-clique C in M. Okay, so it's a totally set with no edges whatsoever. So we can find a countable subset with no edges between any two of its vertices. We can find a countable clique such that for any let me get the quantifiers correctly. So we can find let me write it in the opposite order. So for any given a countable clique C, and an arbitrary subset A subset of an arbitrary fixed power of C, let's say C to the n, we can find an isomorphic copy of this inside M, inside of M, an induced isomorphic copy inside of M. Can find an induced isomorphic copy of C. Okay, I'm not saying it well, right? Let me say it. Let me say it in the original order first. So, given a clique C or an anti-clique, whichever, it doesn't matter. I just want to ensure that there's no interaction between the vertices of C. So, given an countable anti-clique C, subset of M, and any a subset of C to some power n, to some fixed power n, we can find a set of singletons B subset of M. Okay, so note that A is a set of tuples. So
that's a simple question. What is anti-clique?
It's just a set with no edges between any two elements in it.
Okay.
Like sometimes I don't know. There are different people call it different things. Like
whatever. This no edges. Okay.
Right. So this simply means no edges between any two elements of C. Any two elements of C. Okay. And we can find some set B such that the pointer that A is definable from B. Okay. So what am I trying to do here? I'm trying to code a set of a relation of some arity. So A is my relation of arity n. I'm trying to code it by a set of singletons. Okay, I want to code it by a set of singletons in a definable way. Because remember, we know that all sets of singletons are externally definable. This follows just from the axioms of the random graph. But what I want to achieve is also somehow to be able to externally define relations, arbitrary relations as opposed to just arbitrary unary sets. And so here we can find a set B, okay, B such that A is definable in the structure in which I only have, so in the structure M, so I'm taking the reduct of the full Shelah expansion here. I'm looking at the structure where I only have M, I only have C, and I only have B. I only have these predicates. And inside of it, I can define A, an n-ary relation. Okay? So the first step is to somehow, is to choose some way to code a relation by a set of singletons in the random graph. Okay, how to do this? So assume for simplicity that A is symmetric. Okay, and let's just say it's binary and symmetric for simplicity. So assume it's not important, but I just don't want to deal with. I don't want to write a very careful coding argument. So assume A is a subset, let's say, of C2 and symmetric. So it's just a set of unordered pairs inside of C2, right? Okay. Then, if I enumerate the elements of A, so let's say A, let's enumerate it somehow. So say A is equal to A alpha prime for alpha less than omega, right? So remember, it's a countable, C is a countable set. So A is a countable set as well. So I'm given some set of pairs, right? And what I want is to choose B so that a corresponding element is going to be connected just to these two elements and to nothing else. So we choose B alpha such that B alpha is connected to both of these things. So B alpha is connected to A alpha. B alpha is connected to A alpha prime, but not connected to anybody else in C. To anything else in C. Okay. And so I can keep doing it, right? So for each pair corresponding to an edge in A, an edge to a pair in the relation A, I'm just choosing an element which is connected by the edge of the graph of my random graph to precisely these two elements and to nothing else in C. So now I have to be slightly careful here because, as we know, if I start, for example, with a countable model of the random graph, a non-saturated countable model, I can do it for any finitely many elements, right? I can realize any configuration I want in terms of connected, not connected, for any finite set of elements. But here I'm telling you that I can do something for a countable set of elements at once. So the point is, it doesn't have to be the original clique. What I'm doing is actually building a graph like this, and then I'm just going to embed it in my random graph. And the Rado's random graph is universal for the class of all countable graphs, right? So any countable graph can be embedded into as an induced subgraph into Rado's random graph, into any model of Rado's graph. And so I can find a copy of this situation inside of C. Okay, so this embeds. So then this embeds as an induced subgraph into M, right? By universality. It's a universal countable graph. Okay. And of course, and now to go back, how do I recover? So because I told you I can recover A now from this B, right? So it's in a straightforward manner. So because now we have that xy belongs to A, if and only if the formula is say we have to say there exists something in B, which is connected precisely to these two elements. So there exists some z, let's say, in B, so that E of xz and E of yz, right? So this shows that if B was definable, then A is definable as well, right? But remember that all unary sets are externally definable in the random graph by what we said earlier. So from this, we conclude that C and also A are externally definable, are definable in Shelah expansion. Well, sorry, I'm not saying they're externally definable. What I'm saying is that it's definable, possibly with a quantifier, possibly using quantifiers, in the Shelah expansion. So they're both definable in M Shelah. Right? So we see that any binary or any n-ary relation, I mean, this argument generalizes directly to any relation A of any arity. So we see that any n-ary relation on C is definable in the Shelah expansion of M.
Sorry, just one question.
Yes, yes.
So you're assuming A to be symmetric here. Are you doing a simplified argument of the real argument? Just for
it's a slight simplification. Otherwise, you just have to deal with ordered pairs. So somehow you have to be able to say to keep track that this is an ordered pair rather than unordered. But we can imitate this easily. I mean, you can think about it. It's a slight complexification of this argument.
I was guessing there must be some kind of way to remember the order of arbitrary, not necessarily symmetric relations.
That's right. Yeah. A slight variation works for any relation. Here I just picked symmetric to make it a bit simpler.
Okay, yeah, thank you.
Sure. Okay. Okay. So what we see is that conclusion of this first step is that you can find an infinite set and an arbitrary relation on it, and this is going to be definable in the Shelah expansion. Okay. Now, the second part, let us take A. Okay, and this is this is not ideal now for my assumption of symmetric because I want to pick something explicitly non-symmetric, for example. But I mean, I could choose something symmetric as well. But let's say C. So say we enumerate C somehow. So C is going to be, let's say, A alpha for alpha in omega. Pick an arbitrary enumeration of C, and we can take A to be, let's say, the set of all. Let's say the set of all pairs below the diagonal. So we pick all A alpha, B alpha, A alpha, A beta. Sorry, for let's say alpha less or equal than beta. Right? So this is C, and this is my diagonal, and I'm picking, let's say, this as A. Okay, it doesn't have to be this. I could pick any non-trivial binary relation. Okay, now the claim. So remember, we want to show that there's no quantifier elimination here. So what I want to say is that we cannot define this A without quantifiers. Okay, so we saw that we can define it with quantifiers in the Shelah expansion, but what I'm saying now is that we cannot define it without quantifiers. Okay, so why? Because as the theory of the random graph is a binary theory, okay, so it terminates. Okay, one way to say it, I guess, is just eliminates quantifiers in the binary language, right? It has QE just in the language with the edge relation. It's a binary theory. It follows that every externally definable subset. Every externally definable subset of C square has to be of particularly simple form. So it's of the form okay, you can say it's a finite Boolean combination. Finite Boolean combination of unary sets, of sets of singletons, right? So and so products, the Cartesian products. So finite Boolean combination of sets of the form A times B. Maybe I shouldn't use A because I already have A. So let's say it's a Boolean combination of sets of the form X times Y for XY, both subsets of C. And we have the equality also, right? So we also allowed to use the relation X equals Y. So we have the diagonal. So do you agree with this? So again, the theory of the random graph is binary, right? So every formula in any number of variables has to be a Boolean combination of formulas which only involve two variables. So it's a finite Boolean combination of formulas, each of which only has two free variables. But now, if we are looking at an externally definable set, a subset of C square, this has to be defined by some formula. Remember, it's defined by some formula, let's say in two variables, phi of x, y, z, and then we plug some external parameter b, let's say, instead of one of the variables z, right? So it's phi of x, y. But this phi has to be equivalent to a Boolean combination of formulas which are only allowed to talk about xz, yz, and xy separately. Right? So here I'm using that C is an anti-clique because, of course, I have a formula E of xy, which would give the edge relation on the graph. But we chose C so that it would neutralize the edge relation. You see? So, okay, so here, let me stress it. Using that E intersection C square is empty. So I don't have the edge relation on C. And what I'm left with is formulas which talk about X and some additional parameter, external parameter, or Y and some additional external parameter. But each of the sets is unary, it's just a subset of C. And we only can have direct products of such sets and their unions. Well, arbitrary Boolean combinations, but they reduce to unions, right? Because a union of boxes like a conjunction of boxes like this is just another box of the same form. Okay. Okay, but now we are done, right? Because it's easy to see that the set A that we chose here, the set, let's say, below the diagonal, is not a Boolean combination of boxes. So remember, our A was the set below the diagonal, is not a finite Boolean combination of the sets which are rectangles. So rectangles, it means I fix some subset of C here, some subset of C here, and I just have the rectangle corresponding to it. Or I'm also allowed to use the equality formula, so I have the diagonal. But these are the only sets I'm allowed. The only set that I have. And it's a little exercise for you that you cannot build, let's say this, the set below the diagonal, from finitely many sets which are rectangles or just the diagonal itself. Okay, and so what this shows is that we have found some definable set in the Shelah expansion, which is not a Boolean combination of externally definable sets, which are precisely the quantifier-free sets in the Shelah expansion. So this shows there is no quantifier elimination. Okay, does this make sense? I mean, maybe it was a bit fast, so I left a little bit to think about, but it's a neat little argument, which shows that in the random graph, externally definable sets behave badly in some sense. Okay, but now to return to the topic of the talk, actually, that what I want to tell you about is that the situation is very different once we rule out something like the random graph. So, theorem, Shelah, is that if T is an NIP theory, okay, and M is an arbitrary model of T, then Shelah expansion does satisfy QE. Okay. So there's a sharp distinction somehow, which tells us that externally definable sets are much better behaved in NIP theories than without the NIP assumption. So we saw already in the case of DLO, okay, they correspond to cuts somehow, where in the random graph, they basically the arbitrary subsets. And this is one way to make precise that the things are much better in an IP. Now, okay, maybe I should ask the question to the audience. Everybody knows what an IP is, or should I say something about this?
Everybody knows.
Okay, great. Okay, so we have this much better behavior in the case of NIP theories. Okay, so what it's saying? Oh, and an immediate corollary of this is that in particular, the theory of the Shelah expansion is also still an IP. So adding arbitrary externally definable sets to the language somehow does not make the theory worse from the point of view of Shelah's classification. The theory remains an IP. Okay, and this is an immediate corollary, in fact, of the quantifier elimination result. So the quantifier elimination result, as usual, can be rephrased by saying that if you have an externally definable set, let's say you have an externally definable set of pairs, an externally definable binary relation, then its projection onto, let's say, the first coordinate is going to be externally definable. So think about this. This is completely not, there's absolutely no reason for this in general. That if you have an externally definable set of pairs and you project onto one of the coordinates, this should still be externally definable. Yeah, there's no reason for this in general. I mean, it's false in general, as we saw in the example of the random graph. Okay, so this is the motivating theorem for what I want to talk about. More precisely, I want to talk about something actually that I did with Pierre Simon first, which in some sense provides, in some sense, it's maybe an explanation of what's going on in the Shelah theorem. It also allows to do it in a more uniform manner. So this something is what I want to talk about is honest definitions. So okay. So okay. So next topic, honest definitions. So this is a bit of an explanation for what's going on with externally definable sets and how we can see them from the inside. Okay, there are several equivalent ways to say what it is. So let me already, as I already pointed out, we can have an externally definable set, which is defined in many different ways, right? So let's say if I have the same picture, so this is M, some elementary extension N, and we have some set X here. Let's say this is my X, okay? It is possible that it is cut out from N by many different definable sets. For example, we have some Y1, Y2, etc. So that Yi intersected with M is equal to X. And Yi is definable in N. Right? So there can be many different external definitions for the same externally definable set X. And what we want to do is somehow isolate among all possible external definitions. We want to isolate the ones which are better behaved in some sense, and focus on that. And what do I mean by better behaved? This is going to be some kind of directedness. We're going to get some kind of directedness between such external definitions. So to define it precisely, definition. So if I have a set X, a subset of M, let's say to some power K, okay, let this be externally definable. All right. An honest definition, theta of xd of x, where d is some tuple in the monster model in some elementary extension of my structure. So by an honest definition for x, I'm going to mean some formula like this, such that it is in particular a definition. So theta of m d is equal to x. Okay, so it cuts out the same set from m as x. So
I'm sorry, in your definition, should it be D in N or in M?
D is well, here n, but here I just want to talk about an arbitrary external parameter anywhere in the monster. Let's say
Okay,
here,
so this is not well. X is a subset of M.
x is a subset of m, and d comes from anywhere in the monster model.
Oh, okay. So this M is different than the first. The M on the right hand side is not the M in the left hand side. This is
No, this is like m. This is bolt m, the monster model.
Oh, okay. I wasn't aware.
Maybe it's not, is it not visible well? Okay, sorry. Maybe I'll write bar or something.
Fine. Okay.
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 Okay, good. So right. Okay. So first of all, it is a definition for x, right? So I have this first condition, but also I want to say that in some sense it's like a definition that never lies. That's why we have the name honest. So and we have that in the monster model, phi. Excuse me. I want to say that theta of xd implies psi of x for every formula psi with parameters in the small model in M such that X is contained in the set of M points of psi. Okay. So if I draw the picture now, let's say this is my small model M and this is my monster model. Yeah. And I have my set X here. So this is X. So what I want to say is that I have some externally definable set. This is going to be the set of all realizations of theta in the monster. Okay, so this is, maybe let me draw it a bit bigger so I can write on it. So I have theta of the monster, D. So all the monster points of this formula. With the additional condition that if I have any subset definable any formula psi with parameters in the small model here, so that inside of the small model, it contains X. Okay, so this is psi of M, little m, D. Then when I look at all the realizations of this psi anywhere globally in the monster, this definition theta is going to live inside of it. Okay, so honest definitions is requiring something about the behavior, about requiring some additional information about the behavior of my definition theta on points outside of the small model M. It's some global statement about behavior of theta everywhere in the monster. Okay, so this external thing is psi. So if I know that psi contains X inside of M, then it has to contain theta globally in the monster. This has to be true for every psi, which we knew contained X, so that its M points contained X. Then the global points of theta have to be contained in the global points of psi. So in some sense, it's like a minimal, I mean, it's not strictly speaking a minimal in any sense, but the idea is somehow that it's like a minimal definition. That it never lies. If theta says that, if theta holds, if theta thinks that some point in the monster should be in the set, all the formulas with parameters in the small model have to agree. All the possible approximations to X have to agree with it. Okay, so this is the definition. One of the several equivalent definitions. Okay, and so the theorem is that in an IP series you can always find definitions with this property. So theorem, if T is an IP, and moreover, I'm stating it uniformly. So I'm stating it with additional uniformity, which was actually a later theorem. So T is an IP, then any externally definable set X in any model of T admits an honest definition. Okay, admits an honest definition. And moreover, we can choose an honest definition depending only on starting with an arbitrary fixed formula defining X. So moreover, have it uniformly. In the following sense. So if X is defined by some phi, let's say, of MC for some external parameter C, okay, then we can choose theta depending only on phi. So theta of XZ depending only on phi of XY. And independent of the particular choice of the model, of the particular parameter C that I'm using to, so that the C instance of phi defines my formula. independent of all of this, yeah? So theta can be chosen depending just on the formula phi itself. Whoops. Okay. So we have this result. Now, it has a bunch of applications. So applications. Well, so the first application is a uniform version of Shelah's theorem on externally definable sets. And in fact, maybe let me give you a proof. It's a one-line proof now, if assuming you know the existence of honest definitions. And by uniform, I mean here that when we have the quantifier elimination result, right? So this is the theorem of Shelah, the quantifier elimination result for the Shelah expansion. The uniformity here means that if I have some formula with a quantifier, and I want to find the equivalent formula which does not use the quantifier. So uniformity here will mean that this equivalent formula without quantifier can be chosen independently of the model. So for any model, you can eliminate the quantifier using the same exact formula. This is the uniformity, the additional uniformity that I'm talking about. Okay, so let's see how to prove Shelah's theorem now. Okay. So we want to show that adding all externally definable sets, we have quantifier elimination. Okay, so how to do it? So assume we have a set. So let X be some subset, which is externally definable, okay? Externally definable. And let's say I have F. Let this be an M-definable function. Let's say from mk to any other power of m. Let this be an M-definable function. Okay. Then, so I'm stating a slight rephrasement, a slight generalization of Shelah's theorem. Then the image of my externally definable set under this internally definable function is still going to be externally definable. Okay. So in the Shelah's theorem corresponds to the case when this function is going to be just the projection, right? Adding the quantifier is the same thing as taking the projection. So to prove Shelah's theorem, we just need to know this for projections. Of course, projection is always definable without any parameter. So it's always going to be M-definable. What I'm saying is here is something slightly more different. I'm saying that I can take any M-definable function and take an image of an externally definable set with respect to it. It remains externally definable. Right? Okay. So proof. Let's say, let us choose an honest definition. Okay, I'm assuming an IP, of course, here, right? I should stress it. It's false without an IP. So assume an IP. So let us pick phi of xc. Let this be an honest definition for x. Okay. Then we are taking theta of yc to say that there exists x, phi of xc, and f of x is equal to y. Okay, and because of honesty, because of the honesty of phi, we are going to get that this is an external definition for the image f of x. So to test yourself, try to think why it wouldn't be the case if it was just an arbitrary external definition. Like there's no reason for it a priori. But we're going to use the fact that we can choose a non-ness definition to conclude that actually we're defining precisely the image f of x using this formula. Okay, so let's check this. So there are two things to check. First, we had by assumption that the set of m points of phi of xc is precisely x, right? It was so phi wasn't in particular a definition for x. So we have to have that f of x is contained in theta of mc, right? So this is automatic. Doesn't use honesty for this inclusion, but we need to use it for the other inclusion. So now take any point A, let's say, belonging to m to the k, but not in the image of x. So assume we take a point like this, okay? And let us take psi of x to be the formula saying f of x is not equal to a. So note that this is a formula with parameters in M, right? In the small model. So this means we can invoke honesty with respect to this formula psi. Okay. So then we have that x is contained in this formula, of course, right? Because I picked some formula which is not so that the image is not equal to that. Okay. And so by honesty, we have that globally in the monster, phi of xc has to imply psi of x, yes, right? So in particular, we get that not m monster satisfies, this is the monster, satisfies not theta of AC. All right? But A was an arbitrary element, not in the image. And we have shown that theta, it doesn't satisfy theta. So it follows that theta of MC is a subset of f of x. All right. So we needed to use honesty for this to get the opposite inclusion here. So this shows that an image of an externally definable set under an internally definable function remains externally definable. Okay, and so this gives in particular Shelah's theorem. There are a few other applications. Is it okay? Other questions about this argument? Okay, if not, let me mention a couple of other applications of this of honest definitions. So they really seem to be useful when you need to understand something about externally definable sets. So another application is concerned with okay, so we have Shelah theorem. Another application is concerned with allows to give, for example, a new proof of the Marker-Steinhorn theorem. So namely, we have the following: if T is an IP, assume T is an IP and rho-z. So, for example, or minimal. And assume that M is a model of T such that all one types over M are definable. So this is all assumption, right? Assume. And all one types, so types in one free variable over M are definable. Okay. Then also all N types over M are definable. For all N. Yeah. So this is generalization of so this generalizes the Marker-Steinhorn theorem. In the case for minimal theories. Okay. So it's a very useful thing to know, right? In the minimal theories that it's enough to check that all one types are definable. So it's enough to check that all the cuts are already definable. This implies that then all types are definable. So this way we can see, let's say that if you take as a model of RCF, you take the actual reals, you can see from this that all types over them are definable, just because the order is complete. The order is Dedekind complete. So this is a generalization of this. Here the argument is a bit more involved, but again, somehow relies the Sonus definitions in a crucial way. And it applies to some other cases, not just to minimal structures. And let me mention one more application, which is somehow concerned with the most basic property of externally definable sets. So the question is like this: assume I have an externally definable set, which is infinite, right? So assume X subset M is externally definable and infinite. Okay. Then can I find an infinite definable subset of X? So given an infinite externally definable set, is it possible to find an infinite internally definable subset of it? It's like we saw in DLO, right? In DLO, for example, if I have a cut, of course, I can always choose a slightly smaller cut, slightly below, let's say, which is still will be infinite. So in DLO, it is true. I mean, it's obviously true for definable sets of singletons, and it generalizes straightforwardly to subsets of the powers. So it's true, for example, true in DLO. Okay, but what do you think? Is it always possible? I mean, in an IP theory, of course. Without an IP, I mean, we can't expect to say much about this thing.
Yes, my guess is because you stated it is true, but I have no idea how to say it.
Yeah, it's not true. Yeah, it's true sometimes. Okay, so here's an example where it's not true. Not always true in an IP. The example I can give you is let's take M to be let's say just the linear order, but this is going to be my set. Okay, so I take n plus z. So I have the order where I first have a copy of n, and then I have a copy of z following it. Okay, and the structure is just the linear order on it. Okay, so I can take X, so my externally definable set, I will take it to be just the natural numbers. So this is X. Okay, first of all, note that this is externally definable, right? Because I can always find an element which is above any finitely many elements in N and below any finitely elements from Z here, from the copy of Z here, right? So then by compactness, I can find an element realizing precisely this cut between these two components in some bigger model, right? And so then I can just say I'm smaller than this element in the monster, which realizes this cut between the copies. So this will tell me that this first set, the copy of N, is externally definable. Okay? But it's not possible to find any infinite internally definable subset of N. So here you have to check a little bit. So we have QE. If you expand by saying I'm at distance n, right? Like I'm the nth successor and the nth predecessor. if you add, let's say, function symbols for this, then we can show QE in this structure. But then whatever, any subset of n that you can try to define, it's going to be either finite, or by overspill, it's going to contain some non-standard elements from Z. So there is no way to pick out exactly n. Right? So there's a little bit to check, but in this case, yeah, this X is an infinite set, but there are no infinite definable subsets of it. Okay, so turns out one abstraction here is elimination of the exists infinity quantifier. So there are a couple of things I can say about this. So first, some facts. So one, and this we proved with Pierre using honest definitions, is that true if T eliminates exists infinity. Okay, so this is true in DLO, for example, but this of course fails here, right? Because we can have one formula so that different instances of this formula define arbitrary large finite sets. So this is precisely what it means not to eliminate the exists infinity quantifier. But in this case, but if you do eliminate infinity, you can get it. This is always true. So we also were able to show that if you start with a set large enough, you can find an infinite subset. Okay, so what we could show is that if the cardinality of X was not only infinite, but was actually quite large. So if it was bigger than beta omega, or at least beta omega, then X contains an infinite internally definable set. So definable in the in the model M itself. Okay, so if it's large enough, you can find at least an infinite subset. And actually, it was open for a while if one can do better than this. So we conjectured that it's enough to take Aleph1. Okay, so in this example I just gave you, you start with an infinite externally definable set, but you cannot find an infinite internally definable set inside it. So the next best thing would be, let's say we start with an uncountable externally definable set, and we try to find an infinite subset. And this was proved recently, actually, very recently, that this conjecture is true. It is confirmed. So it's due to Bayes, Benaria, Kaplan, and Simon. So we can replace being bigger than beta omega by just being bigger than Aleph1. Okay, so this is now optimal somehow. Well, because of this example, it showed that this is optimal actually. So all of this relies on honest definitions in a crucial way. And let me mention one more application, which actually was one of the main motivations when we started working on this honest definitions. This was a problem actually of John and Benedict. So this is application. Let's see. Application 4, apparently. So this is a Baldwin-Benedict question. Yes. So the question was, assume T is an IP. And let's say you have I. Okay, so M is a model of T. And inside of M, we choose a small indiscernible sequence. When I say small, what I mean is that small with respect to M. So somehow, i.e., let's say M is I plus saturated. One needs less than that, but let me just state it like this. So M is I plus saturated. Okay. Then John and Michael, they showed that you have a certain form of bounded quantifier elimination in such structures. So then, okay, so this is what they proved. So they proved that then the structure Mi, so this means I expand by new unary predicate, which names this indiscernible subsequence. So then Mi eliminates quantifiers down to the predicate. So let me state it like this maybe. Then in Mi, every formula, so I look at it as a structure in the language LP, where I expand L, the language of T, so this was L theory. I expanded by a new unary predicate, and I interpreted by naming this indiscernible sequence, okay? So then every formula, every LP formula, is equivalent to a bounded quantification formula where we only allowed to use quantifier over the predicate, over the sequence. So to a formula of the form, let's say Qx in P, Q1, X1, Q n xn in P, and then some formula, quantifier-free formula in LP. So let's say phi of x1 through xn, and then some tuple of variables y bar. So let me say maybe every LP formula psi of y bar is equivalent in the theory of the pair to a formula of this form where Qi is either a universal or existential quantifier. So Qi is either exists or for all. Okay. And phi of x bar y bar is a quantifier-free LP formula. So this is sometimes called that the theory of the pair is bounded. So all formulas are equivalent to those where you're only allowed to quantify over the predicate, over the sequence. Okay. And the question was if this remains an IP. And so we proved this using honest definitions. So the theory of the pair in the LP language remains an IP. Okay. It's actually important that the sequence is somewhat small. If I allow arbitrary indiscernible sequences, let's say the full size of the model, this can fail. I mean, we have examples in that paper. But you can always name a small indiscernible sequence, no matter the order type. Actually, I think in the paper by John and Michael, they probably focus on the densely ordered sequences or something like this. But the general case reduces to it very, very quickly. Okay, so this is another application. And there's a bunch of other applications. This one's definition seems to be very useful when you want to talk also about pairs, where instead of just naming a subsequence, you're naming something else. Like people studied, there's a whole industry. You, for example, can have a dense pair of minimal structures or like valued fields, etc. There's a lot of such things. And whenever you want to prove somehow that the pair remains an IP, assuming you started with an IP structure, and some additional assumptions, this is always this one's definition seems to be somehow what needs to be used always for these things. Okay, so these are a few applications I wanted to mention. I mean, there are some more. There's also something called uniform definability of types over finite sets, which was closely connected to the question of compression schemes in machine learning. It's a model theoretic version of that. And this uniformity of honest definitions that I stated, it provides somehow the model theoretic counterpart of this problem, of this phenomenon. But let me not say too much more about it for now. Okay, so what I want now is to state as a new theorem. So far I just talked about sets, right? We talked about sets and the external definitions. It seems very interesting. By the way, Rami, when should I stop? At 1/2 past?
Yeah.
Yeah, okay.
You
Yes.
can go over if you want to, but usually people
No,
stop.
I'll try to stop. Yeah. So it's also very interesting to understand this external definable objects with additional structure. So as often the case in model theory, like we understand something about sets, but then you're somehow forced to look at groups. I mean, some people just like to study groups for their own sake. Of course, that's great too. But sometimes also you kind of have to look even if you don't care. So I wanted to say something about external definable groups. Okay. So what is that? So definition. So a group G, let's say with some multiplication operation, let's say times, is externally definable okay. So we are assuming we are working in some structure M model of T. It's externally definable. Well, if both the universe is an externally definable set and the graph of multiplication is an externally definable subset of the power. Okay, so if both the underlying set G and the graph of the multiplication, so I think about it as a ternary relation. So both of these are externally definable sets of some powers of M. Some power, yeah. So I mean, this has to be, of course, then a subset of M to the n cube, yeah. So 3m. Okay. So first of all, we immediately can see that there are new external definable groups which were not already definable. For example, let T be the theory, I don't know, take RCF, real closed fields, take a model M to be somewhat saturated. Let's say Aleph not saturated, let's say. Okay. What I want to look is the group of infinitesimals with respect to the addition, let's say. So let me draw this. Okay. So these are the reals. Sorry, not the reals. This is my structure, my model M, a saturated model, non-standard extension of the reals. Then we can define G to consist of all x in M, so that x is between 1 over n and minus 1 over n for all natural numbers n. Okay. So this is going to be somehow an infinitesimal cut that I have around 0. And note that this is, of course, a group under addition. So then G, with respect to the standard, to the usual addition, this is the addition on the model M, right? Extended by elementarity from the addition on the actual reals. So then this is a group, a type definable group, but it's also externally definable. Okay, so it is both. Well, let me not care about type definability for a second. So this is a group. It is externally definable, right? Because I could simply pick the cuts corresponding to this. So I can pick a cut below everybody, let's say, I can pick a cut below 1 over n for all n, but above everybody else in the model. So I could pick that cut and take some element in the elementary extension, which realizes precisely that cut. And I could pick the same on the left, and then this gives me the interval. It cuts out precisely the infinitesimal part of this model M, using parameters that come from some bigger model from the monster. Okay, and because we define it so it has to be below every 1 over n for all n simultaneously, this is a group, right? under addition, let's say here. Okay, so it is externally definable, but note that unlike what happens in stable theories, let's say, this is not contained in any. Sorry, it doesn't. Yeah, it's definitely not internally definable, right? So not definable. This one can see quickly from using the minimality of the theory, let's say, because definable sets are just unions of intervals with endpoints in M, but this set, of course, is not of such form, right? So we see that this is not definable in M. Okay, so. And we have, of course, many variations of this. Basically, you can take any definable Lie group, real Lie group, and take the infinitesimal part there. These things will, again, be externally definable, but not definable. Okay. So in general, we see there are new externally definable groups. And it's not so easy to understand what they can look like in general. I mean, I don't think currently we will have like good, precise conjectures. I mean, what one would want to say somehow to describe externally definable groups using internally definable groups. Somehow to say that they're connected, that there's some kind of limits or something. But at least I want to state one theorem, which shows that at least we can understand them, or even more precisely, eliminate them under the so-called FSG assumption. So I'll say what it is in a second. Okay, so definition. A definable group. So forget external definability for a second. A definable group G is called FSG. FSG stands for finitely satisfiable generics. Okay. If there exists a type, a global type, concentrated on the group, so it implies the formula defining the underlying set of the group, such that, and the small model, let's say M small, such that all translates of this type P are finitely satisfiable in this model. So such that for all G in the monster, okay, so it's a definable group. So I'm looking at the monster points of G. We have that the corresponding translate of the type G times P is finitely satisfiable in this fixed small model M. Okay. So examples, in a stable theory, all groups are FSG. Every definable group is FSG. This notion actually was isolated in the study of Pillai's conjectures in minimal theories, where they somehow provide an abstract characterization of definable compactness. So if T is minimal, then G is FSG, if and only if G is definably compact. Okay. So if I'm looking at the standard model, at the actual reals, this corresponds precisely to the usual compactness of the group with respect to the topology induced from the ordering in this case. In general, we only require somehow compactness with respect to definable sets, right? And the same is true, by the way, in QP, let's say. So again, definable compactness of the group with respect to the topology introduced by the evaluation this time instead of the ordering is again equivalent to FSG. So it's an interesting notion. Somehow it simultaneously generalizes stable group theory and generalizes compact. Outside of stability, it provides some kind of compactness, an abstract notion of compactness, which makes sense even if you don't have any topology explicitly given to you in the underlying structure. Okay, and I mean, a lot can be said about this. I mean, people study these things a lot. But let me just state the theorem. So the new theorem is the following. So T is an IP. Okay, I have two things. If G or M is a model of T. So first, if G is definable in M, okay, so definable in M, and H is a subgroup of G, which is externally definable, and F as G, but in the sense of the Shelah expansion, okay, then it is already definable in T. Well, in T or in M, I guess I should say. Okay. So the first result says that there are no new FSG subgroups. If you start with a definable group in T, and you have an arbitrary external definable subgroup, which is FSG, so a priori this H, I mean, it's not definable, it need not be definable in T, yeah? It is only externally definable. Then it can be eliminated. Then it's already definable in T itself. So somehow there are no new compact subgroups. This was actually motivated by a question Pantelis Eleftheriou asked me, where the question was specifically for RCVF, for real closed valued fields. Somehow the intuition there was that there shouldn't be new compact subgroups appearing. And indeed, this is true, yeah, even in this level of generality. So this is one, and two is even better. So if now I'm not going to assume presence of any definable group in M. So here this was subgroups, externally definable subgroups of internally definable groups. Now I'm going to say that if G is any group, any group which is externally definable and FSG, so any group definable and FSG in M Shelah, or more precisely the theory of M Shelah, then it is definably isomorphic to an internally definable group. So then it is definably isomorphic. So definably in the sense of the Shelah expansion. The isomorphism itself I might not be able to see from below, but it is definably isomorphic to an M definable group, or more precisely MEQ definable group G prime. Okay, and so this G prime is definable or interpretable in M itself, in the original theory. So any externally definable of such G group is definably isomorphic to an internally definable group. Okay, this is the second theorem. Okay, so there are these two things. Yeah, I don't think I have. I mean, it would be. I can't say anything. Basically, I should finish. It's very open. The situation for groups interpretable in Shelah expansion is much harder, because there you have things like G mod G00, etc. So there, in hyper-definable groups arise unavoidably. I mean, there are some partial results, but this is open in general. So let me just finish with this problem. Describe groups interpretable in the Shelah expansion. Open. But there is a very nice example by Eric Wolfsberg, which shows that you can only see them as hyper-definable groups. It's unavoidable to study hyper-definable groups somehow if you try to understand interpretable groups in the Shelah expansion. Hyper-definable means, let me remind, it just means you have a type-definable equivalence relation. And it's like MEQ, but now your group lives on a quotient by a hyper-definable equivalence relation. It's a type-definable set modulo a type-definable equivalence relation. And in fact, even the proof in this theorem that I stated, it has to go through hyper-definable groups. So it's a bit funny. One has to do first somehow recognize this group as a hyper-definable object in T, and then you can eliminate this thanks to the fact that you started with something externally definable. Okay, and the proof relies on again on the theory of honest definitions, and relies on a new. I have to develop some kind of new group chunk theorem where it is done on a measure, because usually group chunk is done on a type. So the idea that we have a generically given operation which behaves like multiplication in a group, it satisfies associativity, but it's only defined somehow on generic points. It's defined on some type, on some global invariant or definable type. So here I have to do something similar but on a measure. So I'm going to work with the Kistler measure and develop some kind of group chunk on a measure, where you say that the operation is defined with measure 1. And if the measure is nicely behaved, definable, one can build a hyper-definable group out of it. So usually in stable theories in the group chunk, you build a interpretable group, right? You build a type-definable group in MEQ. But here we can only build a hyper-definable group because the equivalence relation now is more complicated. Yeah, so these are two main ingredients. I mean, there's some other stuff that goes in. Okay, yeah, thank you very much. I'll stop here.
Okay. Thank you for this amazing lecture. Could you mention a couple of references?
Yes. Maybe it would be easier actually to send them if I can just send it to the same emails that.
Yes,
yeah.
this is perfect. So just for people, I recorded this lecture, and I will post it on the website of the department next to with the abstract of the lecture with an announcement and the abstract. So at the bottom of the abstract, there will be a link for the recording for people who are interested. And definitely, if you could send a couple of references or more than a couple, it would be very helpful.
Yeah, I'll be happy to. Yeah.
Okay, so it's kind of late, but if anybody has any questions, comments, whatever, can...
So I did actually have a question. Like this presentation seems to be working mostly with like with tuples that are finite. Is there any extension of this into like infinite tuples that are definable somehow in a model?
I see. You mean like sets, but in infinitely many infinite tuples somehow? Yeah.
Yes.
Yes. There is. Right, there is a type-definable version of this. In fact, in some sense, these honest definitions behave even better for sets which are type-definable by small type. So somehow you have a small partial type, possibly using infinitely many parameters. And we can talk about external definability, but now we can talk about external type definability, where I'm allowing my set to be given not just by some formula with an external parameter, but by a formula with by a small partial type with a small set of external parameters. And in this context, actually, there's a precise characterization what external definable sets are. In a precise sense, they're exactly like, for example, unions of directed systems of internally type definable sets. In fact, there's conjecturally something like this should be true for just formulas and honest definitions, but actually that is not known yet. It's still open. But for partial types, this can be done. So for partial types, there is so basically it extends naturally in the partial type definable context. Yeah. But there is more to explore there. Yeah, definitely.
Thank you.
Anybody else? So once again, thank you.
All right. Yeah. Thanks everybody. Yeah.
See you. Bye-bye.
Okay. Bye-bye.
Thank you.
Bye, Remy. Thank you.